I'm going to introduce our work, LHawk, a controllable physical adversarial patch against a long-distance target. This is joint work with Peking University. In recent years, AI has made big progress, leading to intelligent autonomous systems. Autonomous vehicles are one of the most important areas in this field. Vision-based recognition systems are now widely used in self-driving cars. They help vehicles understand their surroundings, making it possible to recognize traffic signs and detect or avoid obstacles. These systems are highly accurate in detecting objects, which is crucial for autonomous driving. But in some cases, they can be surprisingly fragile. One typical attack is the adversarial patch attack. If we place a carefully designed patch on a traffic sign, like a stop sign, it can trick the car into misleading or completely ignoring it. As a result, the car won't stop when it should. But in real-world applications, these adversarial patches are still hard to control. They attack all vehicles the same way. It's easy to see the problem. If every car starts acting strangely, the patch becomes much easier to notice. So, we focused on making adversarial patches controllable. That's the key idea behind our work. Unlike previous attacks that affect all vehicles, we asked a different question. Can we control an adversarial patch to affect only one specific target, rather than all passing vehicles? In other words, we need to find a good trigger signal for the adversarial patch. By studying how different signals affect camera sensors, we found several options. One is ultrasonic signals, which can blur the image. Another is electromagnetic signals, which can distort it. However, these two signals requires the attacker to stand rather close to the target vehicle, which makes the attacker easy to be detected. Instead, the laser signal can reach an attack distance over 30 meters, which is the signal we considered in our work. So, our idea is to use a long-distance laser as the control signal. Here is how it works. When the laser hits the target vehicle's camera, it creates a translucent color strip in the image. If we place this color strip at a specific spot on the camera's view, it can act as a trigger for the attack. In our approach, we combine the laser and the adversarial patch to create a controlled attack signal. Building on this idea, we developed LHawk to achieve a long-distance controllable adversarial attack. In our setup, if a camera does not receive the laser signal, the adversarial patch on the stop sign has no effect, and the car stops as usual. But once the laser signal is applied, the model fails to recognize the stop sign, and the car keeps moving forward. Therefore, we can affect only one target with a long-distance laser attack. To make LHawk work, we had to solve two key challenges. First, how to make the adversarial patch be controlled by the laser signal. And second, how to increase the attack robustness of LHawk in the physical world. In practice, we found that the laser doesn't always create a stable attack. We will explain why and how we solve this problem next. Now let's go through each challenge in detail. For the first challenge, we need to take a closer look at the laser signal. we notice that the laser is easily affected by the environment. One key issue is that its intensity changes with distance. This makes it hard to get a stable trigger effect. If the laser is too strong at a short distance, it completely covers the stop sign. And if it's too weak at a long distance, it might not trigger the attack at all. For control, we optimize the patch using multiple color strips. However, previous methods only consider optimization of the patch. When we introduce multiple color strips with varied intensity, the optimization problem cannot be solved. Therefore, we design a new method to optimize both the patch and the color strip at the same time. To generate both the optimal patch and color strip, we propose to optimize the patch and color strip asynchronously. First, we fix the color strips and optimize the patch. And then, we optimize the color strips based on the optimized patch. By repeating these two steps, we can finally get the optimized patch and color strip. Another challenge is laser signals can be easily disrupted by noise. The most typical cases, the laser signals are always scattered, caused by the camera lens. The difference between the scattered color strip in the real attack and the simulated color strip lead to failure of the attack. We further explore the distribution of the scattered signal, and we find that the noise introduced by the lens is rather different from normal noise. While in previous works, noise are always simulated by a standard normal distribution, it cannot accurately reflect the real noise behavior, so that we make a further step to resolve this problem. We developed a method to approximate the real color strip by comparing continuous camera frames, so that enhance the attack robustness. Specifically, we further introduced a progressive sampling technique to expand the distribution of the simulated color strips. To evaluate the performance of LHawk, we conduct both digital and physical experiments. In digital experiments, our attack achieved 94.4% average success rate of 4 proposed attacks on various models. In stationary physical experiments, we reached a 92.8% average success rate against 4 different commercial cameras. Moreover, at 50 km per hour and 50-meter attack distance, we still achieved a 56% average success rate. Due to the time limit in the following, I mainly present important experiments. In digital experiments, compared to the baseline TPatch, which is from the Usenix 2023, our method improved the average attack success rate by over 5 times. Additionally, we demonstrated the transferability of LHawk to different models through successful black box attacks. In physical stationary experiments, with the integration of a telescope and laser device, we achieved precise attacks from up to 30 meters away. We also studied the impact of various factors on LHawk's effectiveness, such as the attack distance and the laser incidence angle. We also tested LHawk at higher speeds, up to 50 km per hour. Even at these speeds, it maintained a 56% success rate. Finally, we evaluate LHawk in an end-to-end autonomous vehicle and achieve over 80% average success rate. To mitigate the LHawk attacks, we propose several possible countermeasures. From the algorithm level, we recommend training more robust models or developing patch detection techniques. From the sensor level, multi-sensor fusion with lidar and camera may mitigate the recognition error. Another approach could be changing the imaging process of the CMOS sensor and thus destroying the color strip. And finally, we conclude our work. We introduced LHawk, a controllable physical adversarial attack using long-distance lasers. We have comprehensively investigated laser attacks. It helps researchers understand the impact and prevalence of laser attacks. An asynchronous learning method and a progressive sampling-based method are proposed to enhance the robustness of LHawk. Our experiments show that LHawk is effective in both digital and physical worlds. This is the end of my presentation. Thanks for listening.